Hello chip dippers. Now while Family-Fractic takes a long overdue break travelling the globe in search of rare retro tech and TV treasures to share with all of you, call me Indiana Joysticks, we are switching to Retro Recipes co-op mode. Now I'll still be sharing regular updates on the Patreon as we travel around the world, but it is indeed those very same patrons that I'm passing the joystick to, and each week one of them will insert their disc into the Retro Recipes drive and share with you their own brand of retro magic inspired by retro recipes. I think it's a really great chance to spotlight some of those incredible channels out there, give them this platform and let them share what they can do with you. And this week it's all about the program from the past. You'll remember this newfangled contraption, or old-fangled as it really is. We tried to receive a program sent from 1982 or thereabouts on a Commodore 64. And although I got it kind of working, we had to cheat a little bit and use a modern Python script to decode the final stuff. Now, there have been some developments since then. I teamed up with Daniele from Lemon64 again, and he's actually created a program that lets me really fine-tune this, because this potentiometer was so sensitive. And I was able to get a perfect tuning. You can see me here running the alignment program, and this indicates that everything is set up to receive the perfect broadcast. But despite doing everything else correctly, it never would have worked. Why? We actually still don't know. And that is where, by some stroke of incredible timing, that week I got a fax from Mr. Edwin Steiner. And he explained that he'd actually solved the issue, discovered two fatal flaws with the original 4Computer-Buffs circuit diagram. So now we're going to hand you over to Edwin for this Retro Recipes 2-Up takeover. And remember, be kind, no blowing in his cartridge to make him work harder. 2-Up, you're up.
Hello Internet! I'm wearing my almost period correct jacket today because in this video we are going to challenge the C64 to do something quite special.
I'd like to tempt you to take part in an experiment.
In 1985, 4 computer geeks on British television challenged themselves and their viewers to an experiment.
It may seem a crazy idea.
They wanted to see if you can transmit program code for a microcomputer by encoding it in a blinking dot on the television screen. Viewers got some instructions in advance to build a circuit.
It'll probably blow up. Quite harmless though.
That uses a phototransistor to sample the screen and transmit data to the user board of their microcontroller. They also got a receiver program to type in that should capture this data and store it in the memory of the computer. Unfortunately, I have never heard of anybody who completed this experiment successfully. But this made me curious. Could it work in principle? Maybe it just needs a couple of small fixes. And we could make it work. So let's try. Few things are better than receiving new parts for a project. And here they are. Phototransistors, multivibrators, and of course the all-important sucker.
You'll need to build a receiver like this.
Let's see whether we've got everything to build the original circuit. We've got the 74LS123 multivibrator.
It's a bit of a mouthful, that.
The BC108 transistor. The particular phototransistors given in the original component list are the only components not readily available today. Since I do not think that the choice of phototransistor is crucial, as long as it is sensitive to visible light, I chose the Vishay BPW96C, which is easily available and has decent sensitivity. With a 470 kilo ohm potentiometer, a 6.8 microfarad tantalum cap, and a few resistors, our list is almost complete. We just need a 9 volts battery clip and battery, a protoboard and some hookup wire, and we are ready to go. But what about those mystery components? The layout suggested in the magazine article back then didn't really work for me, so I decided to sit down with the pinout of the multivibrator and create my own board layout. While I'm building the circuit, let's briefly talk about how it is supposed to work. In order to transmit a character like A, for example, the numerical value corresponding to this character will be sent bit by turning the dot on the TV bright for a 1 bit and dark for a 0 bit. European TVs of the time refreshed with a frequency of 50 Hz, so the fastest bit time we can achieve this way is 20 milliseconds per bit. But the receiver still needs to know when the transmission of a byte starts. Before the transmission of each byte, a low start bit is sent, and after the transmission of the byte, one or more high-level stop bits are transmitted. Therefore, the receiver can simply wait for this high to low transition, then wait for half a bit time, and then start sampling the signal every 20 milliseconds. This approach of sampling each bit in the middle of the period gives the receiver the maximum amount of margin for timing errors. However, there is a complication related to how CRT television screens work. The TV image is created by an electron beam that scans the image area sequentially. So we will only ever see very narrow and probably irregular pulses of brightness whenever the electron beam crosses the sensor area. This is what the multivibrator in the circuit is used for. Whenever the brightness detected by the phototransistor rises sharply, the multivibrator is triggered and will produce a high level at the output for about 20 milliseconds. If the pulse length of the multivibrator is tuned correctly, it can create an almost ideal signal. If there are bright pulses with a distance of 20 milliseconds, we want to see a continuous high level at the output without any dips in between. On the other hand, the output pulses must not be much longer than the nominal 20 milliseconds, because otherwise, if you have a 1 bit followed by a 0 bit, the high level would be prolonged too much and it would interfere with a reliable detection of the low level for the 0 bit. For the sensor assembly, I drilled a 4.5 mm hole into the suction cup to securely hold the phototransistor. I soldered a twisted pair of wire to the phototransistor and secured it with some heat shrink. To make the suction cup airtight again, I filled it with some bathroom silicone. And that's the sucker completed. Since nobody so far has gotten this circuit to work, I think we should first test it and see if it is at all functional. And for that we will allow ourselves the luxury of some modest test equipment. I'm sure you could do all of this with period correct gear also, but I don't have enough of that. For simulating the TV screen, I have built this test fixture that contains a white and a red LED. Currently the white one is used, and the function generator makes this LED blink with a frequency of 50 Hz, and it is lit only for a very short time. So let's try it. I try to put the sensor exactly over the LED, and indeed we see a pulse train now coming out of the data output of the circuit. The pulses coming out of the circuit are somewhat shorter than 20 milliseconds. I will now turn the potentiometer in order to adjust the pulse width of the circuit. We see it is somewhat adjustable, but it is extremely fiddly. I realized I did a really poor job of demonstrating how fiddly this adjustment is, because on the camera it's not at all obvious how tiny the movements are I make on the potentiometer. With the 470 kilo ohm potentiometer, we get an adjustment range from 6 milliseconds to 1061 milliseconds. We need to hit a smaller than 1% range right near the start of the potentiometer, where potentiometers tend to be even more fiddly. A range of 10 kilo ohms should be sufficient. It is very strange because for the BBC Micro, which of course also expects 20 millisecond pulses, they specified this potentiometer with 22 kilo ohms, which is a much more reasonable value. I took the 470 k ohm potentiometer out and replaced it by a 10 k ohm, and now the adjustment is much smoother. This is working much better now, and I think the circuit is now fully functional.
Hello chip tippers. Let's take a little break from this guy on my channel and talk about something pleasant. Maybe you've got enough of inhaling circuit board dust and ending up with projects looking like this? Then check out our sponsor, PCBWay. Great quality PCBs starting at just $5. And ordering them is so easy. Edwin managed to do it for his weird Pentax project. But look at those beautiful boards. Shiny gold plating, perfect castellated holes. Pretty. But wait, who's that behind you? Get me out of here, buddy. This voice is killing me.
We seem to have a functioning receiver, but what is it going to receive? As you may know from Perifractic's videos, the recordings of the original transmissions that are available online do not have sufficient video quality to make a reception feasible. And the better quality master tapes cannot be shared due to copyright restrictions. So we will have to make our own transmission based on the program data that Perifractic and the Lemon 64 crew decoded. Now, one of the simplest ways to convert this program data into a video transmission would be to use the C64 itself, because the VIC2 chip in the C64 already knows how to generate a good PAL signal. However, putting the program from the past into the C64 first and then receiving it back just does not seem like the right thing to do. We want to have a proper transmission. Therefore, my plan is to generate the video signal using my function generator and an Arduino Nano microcontroller. I wrote a little Python script that adds the required start and stop bits. It also creates this visualization of the whole transmission, showing each bit as a little square. Keep in mind that every one of these about 12,000 bits needs to be transmitted correctly in order to receive the program from the past. It's time to test the circuit with a real signal sampled from a CRT. But the problem is, if I use my trusty 1084S as the TV stand-in, what do I connect my C64 to? Would be good to have another monitor. Maybe I should have finished the restoration of this cute 1404 years ago. I got the monitor working, but using the 1404 was not one of my brightest ideas. Literally. When I tested the circuit with the 1404, I got a total flatline at the output. It did not work at all. Well, I found a workaround that brought it to life. After taking some measurements of the phototransistor current, I was a bit wiser and I had learned quite a bit about both the 1404 and our receiver circuit. The 1404 turns out to be objectively very dim, which surprised me because it looks just fine to the human eye. This is probably related to the amber phosphor of the 1404 having a much longer afterglow than that of a TV or color monitor. I found a way to make the receiver circuit adjustable to a wide range of monitor brightness. I replaced the fixed resistive divider at the base of the transistor with this adjustable setup. This is likely unnecessary if you are using a regular TV or something like a 1084 color monitor. It seems I just picked the worst possible test case. Oh well. Curiously, the 470 k ohm potentiometer is just the right size for this purpose. It really makes me wonder whether this wrongly specified 470 k that makes no sense for the timing adjustment was really meant for something else, and there was some kind of miscommunication in the original design team. Nevertheless, through this detour, I gained a few insights regarding the design of the receiver circuit. I also added a jumper so we can optionally supply this power rail that is originally meant to be 9 volts from the 5 volt supply. The 9 volts is not there to get a larger signal from the phototransistor. The amount of current drawn by the phototransistor hardly depends on this supply voltage at all, at least within a reasonable range. Therefore, I suspect that the 9 volt battery supply was chosen for this supply rail in order to make it noise-free, because it supplies a high impedance part of the circuit that could be susceptible to noise coming from the computer power supply. But wait, you might be saying, what's with all that aluminum foil? Well, right now it's doing nothing, but let me show you something. On the scope, we see the output of the BC108 transistor at its collector. We do have quite a strong signal, which is good, but let me zoom in a bit. If we zoom in further, we see that this noise is not at all random. It has a very particular frequency that coincides with the horizontal frequency of the monitor. But watch what happens when I connect the aluminum foil around the cable to circuit ground using this jumper wire. I made some screenshots for you because I'm not sure whether on the camera you can see the full extent to how much the signal is changing. I should have used a shielded coax cable right from the beginning. Here is how I later built a much nicer sensor assembly using some old microphone wire. This version has shielding up to the first few millimeters of the phototransistor, and it gives an even cleaner signal. I now have the dot on the alternating sequence, and the scope is showing the output of the circuit in cyan, and we can see that the multivibrator does a nice job of cleaning up this irregular brightness signal to an almost perfect square wave signal. I've set up things now so we can test our sensor with another monitor, namely with the Commodore 1084S color monitor. We have the bright dot here that is permanently on, so let's put our sensor over this dot. And would you look at this? Oh my god, it works so much better than with the Commodore 1404 amber monitor. It looks perfect to me, so I think we are ready to go on to the next step and power the circuit from the computer. Will we see any worse behavior with the power coming from the computer? Let's see. Fingers crossed, let's turn the thing on. At least the computer is alive. The circuit seems to work just fine. Now this is awesome. It means that even without adding any additional filtering to the circuit, it should be just fine to power it from the computer like that. We do have a little change of plans. Originally I intended to use the 1404 as a TV stand-in, but now we found that it has quite different characteristics than other monitors and TVs. Furthermore, I found out that we still have a video recorder at home, and this opens up an interesting possibility. The new plan is now to generate the blinking dot signal using the Arduino, to record it on VHS tape, and to then play it back and go from the RF output of the video recorder into an actual TV. This way we have the most realistic reproduction of the TV signal that people would have had back then. Our setup for generating and recording the transmission signal is ready. The function generator generates a combination of vertical and horizontal sync on channel 1 and a pulse for horizontally locating the blinking dot on channel 2. These signals are combined in the circuit I built for this purpose, with an enable signal coming from the Arduino Nano. Explaining the details of this circuit would make the video too long, but if anybody is interested in that, please tell me in the comments and I can share more about that. The output of the combiner circuit goes to the input of the video recorder, and from the output of the recorder, it goes to the monitor so we can visually check the signal. I will now press the record button. Pressing the Arduino button should activate the 1 Hz blinking sequence first. Let's record a few seconds of that. Next we will record the alternating sequence for a few seconds for debugging purposes. Now let's turn the dot permanently on. So let's go. A few seconds of brightness and then you will see the actual data transmission. Here it goes, the magical blinking dot. The transmission should last for about 4 minutes. I timed the original transmission and from that I calculated that probably the original used 3 stop bits per byte. So that's the same that I'm doing here on the Arduino Nano. It's done. The dot has gone dark. The transmission sequence is finished. Let's stop the recording. Okay, the tape has rewound. Let me disconnect the output of this circuit. Now we are sure that no signal is going into the video recorder, so whatever we see is coming from the tape. Let's play it. And there's our 1 Hz blinking dot. That looks good. The alternating sequence. And here tracking problems rear their ugly head. For some reason they were particularly bad when the video recorder was playing back its own recordings. I fiddled with the video recorder for hours, and after many attempts I finally had a recording that played back reliably enough. The moment of truth is getting closer. I have the C64 connected to its monitor and also to the TV through RF. So let's run the tuning program. The tuning program published for this experiment was meant to help the user adjust the pulse width just long enough that for a permanently bright dot, no low levels appear on the user port. The program is very simple. It just samples the user port repeatedly, and if at any time it detects a low-level signal, it puts an asterisk on the screen that remains until it is cleared by pressing a key. We have the dot on the TV, so let me place the sensor as accurately as I can. I will now periodically press a key and increase the pulse width until the asterisk stays cleared. Now, hopefully our circuit is tuned correctly. We could check with the scope, but that would be kind of cheating, right? So let's try it like this. If you enjoy unusual projects like this, you may also like the Pentax Electrospotmatic restoration I did on my channel. There you can also find a version of this video, including a 555-based receiver circuit as a bonus. Even closer to my heart is my quantum mechanics series, in which I give a fresh presentation of the fascinating insights physicists came up with almost a century ago. If you want to understand quantum mechanics beyond the popular level, these videos are for you. So take a look at my physics playlist and please subscribe over at my channel to support what I do. Links in the description. At this point we need to talk about the receiver program a bit. Right after I had seen the first video by Perifractic, I disassembled and analyzed the published receiver program in order to understand how this experiment was supposed to work. Doing that, I found that the published program was missing a crucial piece, the part that is supposed to store the received bytes into memory. Confusingly, only the C64 receiver program had this problem, while the program published for the BBC Micro was complete. Exchanging a few YouTube comments, I learned that users on the Lemon64 forums had already discovered these facts and a user going by the nickname MC513 had already published a completed receiver program for the C64. That is the program we are going to use in the following, because with the program as it was originally published, you would never get the experiment to work. The receiver program should be active now, so let's find the beginning of the transmission on the tape. That is the beginning of the transmission with the permanently on dot. So now all we can do is wait. Oh no, we are having some glitches on the screen. That's really bad because there's no room for error. This receiver software has no kind of error correction whatsoever. So if there's any glitch that is recognized by the sensor, the program is corrupted. Wow, the program exited at about the right time, somewhat above 4 minutes into the transmission. So we have some chance of having received something. Let me now save the received program. Okay, we got an out of memory error. Strange. Let's try listing. Is there something there? Wow, there's a program there. Okay, let's just try to run this program because it looks like we got something. Oh no! It started the banner, but then there is a syntax error, probably because of the glitches. Our program is corrupted. Anyway, it was really encouraging that we got the program at least partially correct into memory. So let's just try again and hope that the glitches aren't as bad this time. I have reset the C64 and loaded the receiver program. Let's start it. Let's start the playback. And press a key. Now let's wait again. You do unfortunately get a lot of glitches again around 3 minutes into the transmission. The receiver exited. So let's see what we got. Saving just doesn't work, unfortunately. Listing looks similar to the first time we tried. Woo! It's working! At least this part of the program is working. Look at that! Press spacebar when ready. Will it work? Will the rest of the program work? A mathematical square. Please type a number between 1 and 100 and press return. Of course, we have to type 42. And we got our magical square. Okay, that was the program from the past. And we actually received it from this tiny television from the past, built in 1968. Amazing. Does it work now? Woo! I think we have it on disk, or rather disk image. Now that I've got into contact with Perifractic, we have a new situation because he provided the digitized master tape recordings. I'm playing them back now here on my Raspberry Pi 400. The signal goes to the HDMI to AV converter, is turned into composite video and goes into the video recorder to be recorded on tape. I couldn't get the Videolan player to play back the interlaced video correctly, so I ended up extracting all the individual video fields from the video and encoding them back together into a video with 50 progressive frames per second. This is the video now being played on the Raspberry Pi, and the image jitters a little bit up and down due to the deinterlacing, but all the frames are correct for the blinking dot. In fact, all the bits are as expected in the transmission except for the first stop bit that is always 0 in this transmission for some reason. But this shouldn't make a difference to the receiver. I had to repeat the recording with my PC playing the video because it turns out that the Raspberry Pi stuttered too much. That means it sometimes repeated a single frame. You would never notice this with the bare eye, but it is enough to completely destroy the reception. Even the PC sometimes seems to repeat frames, but I think I got a good recording now. I'm playing it back on the 1084 because the little TV is so small that the background image comes too close to the sensitive area of the sensor and interferes with the reception. The transmission is finished. Now let me switch the monitor back to the C64 to see if it works. Let's switch to S-Video. Okay, did it work? Do we have a program? Let's list it. Oh, that looks good. Let's run it. Yes, it works. We don't need the sensor anymore. We do have our mathematical square program. And with this, the circle is completed. From the 1985 TV studio to the master tape to a digital video transferred on the internet, then played back, recorded to the analog videotape, played back again and received with our receiver circuit from the monitor. Amazing. The problems we had with saving earlier are probably due to the state of the BASIC interpreter being messed up after the program is injected into memory. It seems to repair itself after running the program. Now that the program is saved, we can also compare it to the original data we sent. And it turns out to be identical bit for bit. Our reception was 100% successful. I think the original experiment would have had a fair chance of success if it wasn't for the two showstoppers we found. The C64 receiver program was missing a crucial part, and the wrongly specified potentiometer would have made it almost impossible to tune the circuit correctly. It's strange that both of these problems affected only the C64 version of the experiment, and I wonder whether BBC Micro users had better luck with their reception attempts back then. Despite its imperfections, it was a very fun and inspiring project the four computer buffs came up with back in 1985, and they deserve a round of applause. Big thanks to Perifractic for reminding all of us about this wonderful episode in microcomputer history. To user NC513 on Lemon 64 for providing the completed receiver program, and to my friend Ernst for borrowing me this cute TV. For more details, contact me in the comments and take a look at the GitHub repo linked in the description. Thanks for watching.
One man can make a difference, Perry. Or one woman. Or dog. The Fractics, lone curators in a vintage world. The world of retro recipes.